going to learn about something called the standard matrix of a linear transformation. So the idea here is that we can write out a linear transformation in this kind of function notation where you've dealt with in other classes here. This one's saying that you take an input point x, y, and your output point is going to be defined as 2x plus y and then x minus 3y. That gives you your two coordinates there. However, we can actually rewrite this function as this matrix 2, 1, 1, negative 3 times an input vector x, y, and you can just double check that if you multiply that vector and that matrix, you get the same output function there. And this matrix here, that's going to be called the standard matrix for the function. Now, whenever you have a function between R2 and R2, R2 and R3, things like this, you can just, write it as a matrix by looking at the coefficients without any problem. But what if we have a linear transformation in other more exotic vector spaces? For example, it's a linear transformation whose input is a matrix and whose output is a matrix, or polynomials or functions. Turns out there's going to be a general procedure in order to find the standard matrix, which is described here. So the idea is we take our input vectors, we look at a basis for those input vectors for the domain, we plug each one of those basis vectors into the function, we get an output, then we take the output and we write it in coordinate form based on the output basis and turn that into a column vector, and those columns then become the columns of the standard matrix. So here's a more exotic function here. It's a function whose input is a second degree polynomial and whose output is a two-dimensional vector, and specifically the two-dimensional vector, the x-coordinate, is what happens when you plug in 0 into the polynomial, and the y-coordinate is what happens when you plug in 1 to the polynomial. So you always have to start down with what is a basis for the input, in this case p2. We know the basis for p2 is x squared, x, and 1. We're going to plug each one of these into our function here. So my function is supposed to take a polynomial, and it's going to output a point here. And so what do I do here? So I'm going to first plug in 0. So if you plug in 0 into the function x squared, you get 0. And if you plug in 1 into the function x squared, you get 1. And so we're then going to turn this into a column vector, and I would get 0, 1 there. Next up, I'm plugging in the next basis vector, which is x. If you plug in 0 in for that, you get 0. Plug in 1, you get 1. So this is once again going to be 0, 1 here. And finally, if I plug in the constant polynomial 1, well, if it's constant 1, it doesn't actually matter what we plug in here, so we're going to get 1, 1. And if you go ahead and put all those as the columns of a matrix, this right here is going to be the standard matrix for this linear transformation. So again, you take each of your basis vectors, you plug it in one at a time into your linear transformation, you take all your outputs, write them as column vectors, and put them together to make your standard matrix. And then once you have your standard matrix, you can get a lot of information here. So for example, if I were to take the matrix that we just had there, and I was going to do some row operations here. Let's see, first I would go ahead and swap. So row 1, swap row 2. And at this point in time, not much we can really do here. Notice that we have a rank of 2, and the nullity, there is one free variable here. So that means the nullity is going to be 1. So the nullity is 1. That means it is not a one-to-one function. However, the rank is 2, and that is the same as the dimension of the output, so therefore it is onto So by finding the standard matrix, we can answer the question of 1 to 1 or onto just by doing row operations. Now our next example here, I'm giving you, hopefully I think, a little bit more interesting example. I'm taking an input of a second degree polynomial, output of a first degree by just taking the derivative. So if you haven't seen calculus, then you can kind of skip this example right here, but I think it's a cool example. And we're going to start with our input basis here, which is still P2, so it's still the same thing, x squared, x, and 1. And if we plug in x squared into our function, we are going to get 2x, and that is the same as 2x and 0 constant, right? Because we're writing our output in terms of P1 here. Then we plug in x into our function. The derivative of x is 1, which is 0x and 1 constant. And lastly, we do f of 1 is 0, and that's 0, 0 there. So the standard matrix for this one would be as so. And then again, once you have this, you can ask yourself, is it 1 to 1, onto, and so on, all based on this matrix here. Now, this last example is something I think is going to be really cool. So we go ahead and we're going to try to do composition here. So f circle g of xy, that means you first plug in the point into g, and then you plug the output into f. So the output of g is going to be 5x plus 2y minus x plus y. And then what do we do here? So it's going to be 2 times the x coordinate plus the y coordinate. So 2 times the x coordinate plus the y coordinate. And then the x coordinate minus 3 times the y coordinate. So that's going to be 5x plus 2y minus 3 times the y coordinate. Okay, so let's see here. 10x minus x is going to give me a 9x. 4y plus y is 5y. And then 5 plus 3 is 8x. And 2y minus 3y is minus y. So it was a little tedious, annoying calculation here, but I do want to point out something that's, I think, really interesting here. If you were to write out the standard matrix of the composition here, you get 9, 5, 8, negative 1. And then I'd like you to go ahead and check for me that if I take the standard matrix for f, and then take the standard matrix for g, and if you were to multiply these here, you should in fact get the standard matrix for f circle g. And so why do I think this is cool? This right here is explaining why you had the really weird rule for how to multiply matrices, how you had to take a row here and a column here and do all this multiplication, addition, and all this big mess here. And the whole point of that, the whole point of teaching you that long, messy method, and the reason why we chose to make it that way, is so that we have this thing here true. So that if you're doing composition of functions, that will correspond perfectly to multiplication of matrices.